Hello everyone. In the last class, we talked about induction machines. So today we'll see the last topic of the machines, that is synchronous machines. So let's start with the topics in the synchronous machines part. First, we have basics of synchronous machines, where we'll be talking about the construction of salient pole and cylindrical rotor synchronous machines and the EMF equations. Later, we have the synchronous machine armature reaction. After that, we'll be talking about the voltage reaction. We'll be deriving some of the voltage regulation expressions. Topic 3. After that, we have synchronous machine open circuit characteristics and short circuit characteristics. These are a part of the methods to determine the voltage regulations. And then we have a two reaction theory, which is used for silent pole synchronous machines. That is topic 5. After that, we have a power flow equation derivations followed by synchronous motors. Let's go to the first topic, that is basics of synchronous machines. There are two possible operations of synchronous machines, that is synchronous motors. The other one is the synchronous generators or alternators. Based on the construction, classified into two types. See the salient pole. Constructions like this. As low speed alternators. Due to the mechanical stability issues, they can't be run at high speeds. That's why they used to be run at low speeds. That's the reason they are called as a low speed alternators. The diameter of the rotor is greater than the length of the rotor, a silent pole alternator. Diameter is C. This is the diameter. Circuit, this is the diameter. This is the length. From here to here is the length. So generally the diameter is greater than the length of the rotor. And the placement of the winding. So the winding construction is a concentrated type. Winding construction or the placement of winding on a rotor is concentrated winding. So we'll see what are the types of windings later. In silent pole alternator, damper windings are used. these damper windings are additional windings which are placed in the slots in the poles like this. So, okay, these are damper windings. So damper windings, why we use damper windings is to eliminate hunting. Damper windings are used to eliminate hunting. So damper windings are the bars inserted in the pole shoes of the rotor. What are the eliminate hunting? Generally, the main reason for hunting to happen, hunting is nothing but the machine rotor gets oscillation. The main some of the reasons for the hunting of in a synchronous silent pole machine is due to sudden changes in load, sudden changes in load or supply, or sudden changes in the field excitation system. That is here, this one, and load containing harmonic, the load containing harmonic parts. So, how are the methods to eliminate hunting? One of the methods is by using damper windings. The other method is to keep a flywheel by using flywheels. These flywheels generally are connected at the end of the machine like this. So these are the flywheels. So the shaft of the we'll go to the next slide. So this is what I have discussed in the earlier slide. What is a salad for the operation of synchronous machine, classification of synchronous machine based on structure, why we need a damper winding in a silent pulse synchronous machine. We'll talk about the cylindrical rotor sync machines. So cylindrical rotor alternator. Cylindrical rotor alternator looks something like this. So we're having the structure. So here on this, there will be slots. Slots will be made on this cylindrical structure. Okay, in these slots, we'll place the windings. Okay, cylindrical rotor alternators. So in case of cylindrical rotor alternators, the field winding, in case of silent pole, field winding is concentrated. So the area is not uniform. In case of the cylindrical rotor alternator, the field winding is distributed, not concentrated type. And these cylindrical rotor alternators are also called as turbo alternators because they can be driven at a high speeds. So generally the number of poles in most of the cases for the cylindrical rotor alternators is either 2 or 4. So here we know there is no need of the damper windings because the rotor structure is mechanically well balanced. Let's see the armature winding classification. So let's see some of the terms. So this is a single turn coil. Okay, this is one side of the coil. This is the other side of the coil. This part is called overhang. This is one side of the coil. The other side of the coil. So distance between these two sides of the coil is called as a coil span. So if coil span equal to 180 degrees, then it is called full pitched coil. This can also be given by slots per pole. So if coil span is less than 180 degrees, then it is short pitch coil. Okay. Now there is one more term called slot slot angle, slot pitch or slot angle gamma. Generally, this is given by 180 degrees into number of poles by slots. Number of slots. For example, if we have three-phase two-pole machine with 12 slots, then slot angle equal to slot pole is H by P equal to 12 by 2. So that is 6. So 180 by 6 is 30 degrees. So the slot angle is 30 degrees. Then the electrical angle theta E is given by P by 2 into theta M. This is the mechanical angle. P is the number of poles. So generally short pitch windings are used to eliminate dominant harmonics. Pitch windings are used to eliminate dominant harmonics in the induced EMF. Okay. So when the rotor rotates, so on the stator there will be an EMF induced, right? So if you have a short pitch winding on the rotor, this can help eliminate the dominant harmonic induced EMF in the stator. So here we are using distributed winding. Generally, distributed winding is used to eliminate higher order harmonics. Higher order harmonics. So in a cylindrical machine, each curve represents a slot, right? So as number of slots increases, what happens is the harmonic content in the EMF decreases because the distribution becomes uniform sinusoidal. There is one more factor called factor Kp. Which factor Kp is given by cos n alpha by 2, where n equal to 1 for fundamental frequency. So if pitch factor Kp, pitch factor Kp equal to 1, then it's called full pitch winding. Pitch factor Kp is less than 1, then it is called short pitched winding. Actually, this pitch factor and all it comes in the induced EMF expression. Actually, that we'll see in the latter phase, yes, latter slide. Generally, the induced EMF is given by 4.4 Kp n kdn phi f, and n is a number of turns frequency flux. This is a pitch factor. This is a distribution factor. Okay. So span is a function, right, and equal to 1 for fundamental EMF component. But if you want to eliminate, suppose, let's say I want to eliminate the nth harmonic component in the induced EMF En. For that, if I make Kpn 0, then En will be 0, right? So Kpn equal to 0, which implies cos n alpha by 2 equal to 0, which means alpha equal to 180 degrees by n. If you construct the machine in such a way that alpha equal to 180 degrees by n, we can eliminate the, supposedly I want to eliminate, can eliminate the nth harmonic from the induced EMF expression. Okay, let's go to the next slide. This is what I have discussed in the earlier slide. So for a short pitched winding, So slot angle alpha to eliminate nth harmonic is given by 180 degrees by n. Similarly, the coil span to eliminate this nth harmonic component in the EMF is given by 180 degrees minus 90 degrees by n. The coil, right? The distance between these two sides of a coil is 180 degrees, then it is full pitch. If it is less than that, then it is called a short pitched winding. So what are the advantages of this short pitched winding? First, that as the distance between decreases means the copper requirement decreases. So it's in reduced copper losses. And it is used to eliminate dominant harmonics. Better voltage regulation. Better regulation. And the disadvantage is we know that E is a proportional to Kpn, right? So if Kpn decreases, E decreases. So because of the short pitch winding, Kpn will be less than 1, so because of which E decreases. So the disadvantage is reduce or reduction of fundamental voltage. There is one more winding called distributed winding. Distributed winding. So for a three-phase machine, there is one more term called phase spread. Phase spread. If phase spread is equal to 60 degrees, then it is called narrow phase spread, which is widely used. And if phase spread is equal to 120 degrees, then it is called wide phase spread. So wide phase spread is used to eliminate triplen harmonics. So what are the advantages of distributed winding? Advantages. The induced EMF will be more sinusoidal in shape. Sinusoidal in shape. Second, the armature winding will be well balanced mechanically. The disadvantage is the same as the short pitch winding, that is reduced fundamental voltage, because the distribution winding, there is one more factor called distribution winding factor KPN. So this is E is also proportional to KDN. Since it is less than 1, a fraction of induced gets reduced. That is one of the top. Let's go to the next slide. So this is what I have discussed. So the slot angle to eliminate nth harmonic and the coil span to eliminate the nth harmonic, distributional winding, advantages and disadvantages. So now let's talk about concentrated winding. Concentrated winding. Generally it is used in salient pole machines. So concentrated winding. If slots per pole per phase equal to 1, then it is a concentrated winding. If slot per pole per phase is greater than 2, then it is called distributed winding. So earlier I talked about distribution winding, right? There is one more factor called distribution factor, that is called KDN. It is given by sine m gamma by 2 by sine and gamma by 2. So gamma equal to 180 degrees by slot per pole. So here n equal to 1 for fundamental EMF component. So for a concentrated winding, KD will be 1, and for a distributed winding, KD will be less than 1. That induced EMF depends upon KD, and right? So we can also write KVA rating of a synchronous machine, which is proportional to E, and that is proportional to KD. So is proportional to KDN. Similarly, the output power of a synchronous machine, is also proportional to KD. And the EMF generated is proportional to KDN and number of turns per phase. Let's go to the next slide. This is what I have discussed in the earlier slide. Next, we will talk about the winding connections, that is star connected winding and delta connected. So let us say we have a star connected armature winding. The rotor, the winding is connected in the form of a star. So let's say this is R phase, Y phase, B phase. So due to the non-sinusoidal flux distribution in the air gap, the induced EMF in the stator will be non-sinusoidal. So it will have harmonic components, say fundamental plus triple and harmonic plus and so on. Okay, similarly, EY will also have EY1 plus EY3 plus and so on. So we have a harmonic component of EMF in the phase voltages. If you take the line voltage, E line to line, which is a difference of phase voltages, let's say ER minus EY. So what happens is these third harmonic components generally are equal in magnitude. They don't have any phase difference, so they will get cancelled out. Because of which in the line to line voltage, there won't be any triplet harmonics. So harmonics are present in the phase voltages, not in the line voltages, the star connect. So and here also the insulation cost is less in compared to delta connector. And there is a possibility of neutral. This is the neutral point, which is available. And we have delta connected armature. So we have a delta connected winding. What happens is, so here also we have harmonics, say ER1 plus ER3, EY equal to EY1 plus EY3. Since here we have a closed path and these harmonics are equal in magnitude and with zero phase shift, what happens is they will get at each other, and because of this induced EMF, as there is a closed path, there will be a circulating force. Circulating current flows in a delta winding due to the triple and harmonics. Okay. So triple N harmonics are present in both line as well as a phase in case of a delta vented winding. But if you select the phase spread equal to 120 degrees, we can eliminate the triple N harmonics in both delta as well as in star connected winding. So why we are getting this harmonics in the induced EMF harmonics. Harmonics are produced due to the non-sinusoidal flux distribution in the area. Okay, so there are two types of harmonics. One is space harmonics, the other one is slot harmonics. Space harmonics are of the order 6k plus or minus 1, where k equal to 1, 2, and so. The slot harmonics are because, see, if you see the armature winding, we have on the rotor, we have slots, right? You see, this is stator and this is rotor. Here there is air gap is more, here it is less. So due to this variation in reluctance caused by the slotting of the stator and rotor, slot harmonics are produced. And these slot harmonics can be eliminated with a fractional slot winding or by skewing the armature slots. Okay, let's see a few example problems. This is what I have discussed in the earlier slide. Here 2001 question. Let's try to solve this question. It is desirable to eliminate fifth harmonic voltage from the phase voltage of an alternator. The coil should be short pitched by an analytical angle of. So we know that pitch factor Kpn equal to cos and alpha. This becomes zero. That particular harmonic will be eliminated from the induced EMF. So then alpha will be 180 degrees by n. So they want to eliminate fifth harmonic, right? So it is 180 degrees by. So it is 36 degrees. So the coil should be short by an analytical angle of 36 degrees to eliminate the fifth harmonic voltage from the phase voltage of an alternator. Okay, let's go to the next topic, that is EMF equation derivation. And then we'll also talk about the armature reaction. EMF equation. So the induced EMF in the armature winding of a synchronous generator is given by the following expression, that is E equal to 4.44 Kp pitch factor, distribution factor, phi flux, and number of coil turns. F is a frequency. So phi is a flux per pole. This is flux per pole. N is a number of turns per pole. F is a frequency. Kp is a pitch factor. Kd is a distribution factor. Frequency of synchronous generator is given by F equal to ns into number of poles by 120. This is the speed at which the rotor is rotating. Next, we will talk about armature reaction. Armature reaction. What is the armature reaction? The effect of armature flux on the main field process is called as an armature reaction. And this armature reaction depends on the magnitude of load as well as load power factor. So let's say this is our flux factor. So on the rotor. So because of this, there will be an EMF since the rotor is rotating, and this the windings on the stator. There will be an EMF induced in the stator. So that EMF will lag this flux by an angle 90 degrees. Now let us consider on the stator we have a resistive load. So the stator winding to a resistive load. That's how the closed path will be completed. So current flowing through the stator winding will be in phase with the induced EMF because it is a resistive load. So IA is the stator winding current. That is nothing but the armature winding current. That gives armature flux. So if you see here, the armature flux is 90 degrees apart from the m. So this kind of effect is called as a cross magnetization effect. Cross magnetization effect. So in case of an generator, the effect of armature reaction for resistive load is cross magnetization. Suppose if you take a motor, still it will be cross magnetization. Now let us consider an inductive load, pure inductive load. So this synchronous generator is connected to a pure inductive load. So this is phi m, this is the induced EMF E, lags phi m by 90 degrees. Now this induced EMF is on the stator which is connected to a pure inductive load. So the current flowing through the stator lags the E by 90 degrees. So this is IA. So flux will be phi A will be in phase with IA. If you see here, it's phi m and phi A are exactly in opposite directions. So this effect is called demagnetization effect. And if it's capacitive load, it will be magnetization effect. Suppose if we have RL or RC load, then we have both RL load, we have both demagnetization and cross magnetization. RC load, we have both magnetization and cross magnetization. This is for the generator. If it is a motor, all things will be reversed. Suppose if you take an inductive load, so the effect of armature reaction in a generator when we have an inductive load is demagnetization. The same in case of a motor will be magnetization. Okay. Let's go to the next slide. So this is what we have discussed in the earlier slide. EMF expression and effect of armature reaction. Yeah, the correction. Correction is suppose if we have a demagnetization because of which the net flux decreases. So what we will do is we'll increase the current so that the flux Im will increase. Im will be the same, so the net flux will increase. So that is the connection needed. So let's try to solve this question. A 24 alternator is having 180 identical stator slots with 6 conductors in each slot. All the coils of phase are in series. If coils are connected to realize single phase winding, the generator voltage is V1. And if the coils are reconnected to realize a three-phase winding, then the generator is voltage is V2. So assuming full singular winding, they're asking ratio of V1 by V2. So what they're asking the induced EMF per phase, if it is a single phase winding to induced EMF per phase, three-phase winding. So this is nothing but KD 180 degrees, that is the distribution factor. KD 60 degrees into turns per phase, single phase by turns per phase, three phase. So KD 180 is given by sine 180 degrees by 2 by 180 degrees. KD 60 is given by sine 60 degrees by 2, here 60 degrees. Turns per phase single phase will be T by 1, turns per phase three phase will be T by 3. So if you solve this expression, we'll get the ratio of single phase voltage for a single phase to the three phase winding is let's go to the next question. A 4-pole 50H synchronous generator has 48 slots in which a double layer winding is kept. Each coil has 10 turns and is short pitched by an angle of 36 degrees electrical. That is nothing but alpha. They have given us the alpha short pitched angle. The fundamental pole is 0.025 Weber. The line-to-line induced EMF for a three-phase star connection is they're asking us to find out the line-to-line induced EMF. The induced EMF per phase is given by 4.44 kp kd by f turns per phase, right? So they have already given alpha equal to 36 degrees. Now the pitch factor kp equal to cos alpha by 2. One because we are considering fundamental induced EMF. So that is cos 36 degrees by 2. So that is 0.95. So we have division factor AD, that is sine m gamma by 2 by m sine gamma by 2. So m equal to slot per pole per phase. That is 48 slot we have, per pole is 4, phase is 3. So that is 4. So if we substitute here sine 4 gamma is given by 180 degrees by slot pole, right? Slot per pole is 48 by 4, 12. 12 into 180 degrees, 12 by 120 degrees is 15 times. So 4 into 15 degrees by 2 by 4 into sine gamma, that is 15 degrees by 2. So this gives you around 0.15. So if we substitute all this, we will have EP equal to 4.44 to 0.95 into 0.15 into flux is 0.025 Weber into frequency 50 turns per phase. Turns per phase is they have given us 48 slot, right? 48 into number of turns is 10 is by 3 turns per phase. Okay. So if you solve the expression, you will be getting the induced EMF. Let's go to the next slide. Let's see this question. This topic is voltage regulation. So generally, the induced EMF in a synchronous machine is given by V plus IR. V is a terminal voltage across the alternator, okay, plus J times IA XL plus J times IA XA. This is leakage reactance drop. This is armature resistance drop. This is armature reaction drop. So if you look at phasor diagram, it will look something like this. So let's say this is our main field MMF phi. We know that the induced EMF lags this by 90 degrees C. Let's say our terminal voltage is V and current is lagging terminal, say lagging load we have IA. Now then, so V direction of IA. IARA is this drop. Then we have IA excess. Actually, that is nothing but V plus IARA. If you take J IA common, then we have XL plus XA. This is called as excess, that is synchronous reactance. Because together we can write E is equal to V plus J times IA. Sorry, take IA common, that is RA plus J times XS, right? So that is V plus IA ZS. The other way of writing the expression for E is equal to, from phasor diagram, E is equal to square root of V cos phi, this is the load power factor, plus IARA square whole square plus V sin phi plus or minus IAXS whole square. So plus or minus it depends upon the type of a load. Is it a lagging load or the leading type of a load? Okay. So now voltage regulation. What does the voltage regulation mean? Voltage regulation is a ratio of change in terminal voltage to the rated voltage when the load is suddenly taken off. It is E minus V. That is a change in terminal voltage to the rated voltage when the load is suddenly thrown off. That is by V into 100. If you take the voltage regulation for UPF as well as lagging power factor, it is always negative, whereas for a leading it is positive. To the next slide. So this is what we have discussed in the earlier slide. So we have there are two main characteristics in a synchronous machine. One is open circuit characteristics. So this open circuit characteristic is nothing but dot drawn between the induced EMF E and the field current IF. Constant speed, okay, at constant speed. means the alternator is running at a constant speed. So this will look something like this. Here it's not, though they are increasing the field current, the induced EMF is not increasing because it is due to the saturation. The other one we have SCC, that is short circuit characteristics. Short circuit characteristics is a plot drawn between the short circuit current ISC and the field current. Generally it looks like a straight line. So this is also drawn at constant speed. Under short circuit condition, the field current or the field current required, that is the field current which is used to generate a voltage for compensating drop due to armature reaction. That's all for today's class. In the next class, we'll talk about the methods to find out the voltage regulation.